What is the nature of reality? In 1927, Georges Lemaitre, a Roman Catholic priest and physicist, first proposed the Big Bang theory. Time and space and everything else in the universe is believed to have started from a singular tiny incredibly hot cosmic explosion. As this fireball expanded and cooled, fundamental particles condensed out from it to form the stars and galaxies that we see today. In this video we are going to look at the history of this Big Bang particle and space view of reality. And we are going to look at some of its flaws. We will then look at an alternative cosmology. This is based on a quantum process that creates the boundaries that we see all around us. We will find that this cosmology has many advantages over the Big Bang particle and space cosmology. Not least that it explains the universe with just one force of nature, predicts radioactive decay and allows the force of gravity between two objects to be calculated using electromagnetic principles. It also gives a concise explanation for the nature of life and consciousness. But this is the subject of other videos on this channel. We are getting ahead of ourselves. We need to justify these claims. Let's start with the history of the search for reality. So the idea that matter is made from atoms dates back to at least 400 BC, when Democritus, a Greek philosopher, suggested that matter was made from indivisible and indestructible building blocks that he called atoms. He believed that atoms were uniform, solid, hard, incompressible, and indestructible. The size and shape of an atom gave them different properties, and so these atoms built the different types of matter that we see around us. All this matter made from atoms floated around in a void, that we would nowadays refer to as space. Fast forward 2,200 years to about 1800 CE, and John Dalton comes to a view of atoms that is very much like the ideas of Democritus. He too believed that atoms were indivisible and indestructible. However, Dalton was a scientist and had good reason for describing atoms in the way that he did. For instance, he introduced the idea of relative atomic weights, and described how atoms combined with each other in simple ratios to make chemical compounds. These atoms of Dalton and Democritus can be thought of as the first generation of fundamental particles, the building blocks of matter. However, about 100 years after Dalton, the physicist J.J. Thomson discovered the electron. And the fundamental nature of atoms was broken. Thomson's view of the atom was known as the plum pudding model. Negative electrons were thought to be dispersed within the positively charged atom. In 1911, Ernest Rutherford discovered the proton and the fact that most of the atom was empty space. And in 1913, with Niels Bohr, they formulated a joint model of the atom that is still used in teaching today. It consists of a positively charged central nucleus that has most of the atom's mass, and very small orbiting, negatively charged electrons. These can take on orbits of different diameters, and so absorb and emit certain wavelengths of light. At this point in history, we can say that we have two elementary particles, the proton and the electron. It didn't take long for a third elementary particle to be discovered. In 1932, James Chadwick discovered the neutron. It was recognized that atoms of the same element could have different numbers of neutrons, and these atoms were called isotopes of each other. This opened up the era of nuclear science, that led to the development of nuclear power and the less useful hydrogen bomb. Since Chadwick's time, a huge effort has gone into trying to understand what builds protons and neutrons. And so, after some 2,500 years, we are still asking the same question that Democritus was trying to answer. What are the fundamental building blocks of the universe? Here is a diagram of the standard model of particle physics. It is incredibly convoluted and complex. Luckily, we are mainly interested in the building blocks of atoms that make up our material world. So third down on the left we have the electron. It is one of a family of 6 particles known as fermions. And it is by far the most stable, with a half-life in the order of 7 times 10 to the 28th years. That is a 7 with 28 zeros after it. In contrast, the muon and the tau have half-lives of less than a millionth of a second. The stability of the electron neutrino has never been measured but is theorized to be stable. The muon and tau neutrinos are theorized to be unstable. So in terms of the matter we see around us, only the electron and its electron neutrino are significant. And as the electron neutrino is known to rarely interact with matter, this too is of limited interest. The electron, of course, is of huge interest. Electron orbitals define the space and the shape of atoms and molecules. Their interactions are the basis of all the chemistry that goes on in the universe. And the basis of carbon-based life as we understand it. Now, besides having comparatively huge electron orbitals, atoms have tiny positively charged nuclei. And although this picture of the atom looks wonderful, it is fraught with problems. For instance, wires-like charges attract. Do the negatively charged electrons not just crash into positively charged nuclei, annihilating the atom? It was not until the invention of quantum mechanics, first proposed by Max Planck in 1900, and developed by Niels Bohr, Erwin Schrödinger and others in the 1920s, that a satisfactory explanation for why this didn't happen was accepted. Essentially, the solution was to confine electrons to discrete energy levels. This keeps them, largely, outside of the nucleus but still accounts for the absorption and emission of light. There remained, however, the huge problem of why the electric repulsion between positively charged protons in a nucleus doesn't just blow the nucleus apart. Or indeed why protons themselves don't just blow themselves apart. The solution put forward by the Japanese physicist Hideki Yukawa in 1935 was to propose another force, different from the electromagnetic force, that would confine protons as well as the neutrons inside nuclei. Unsurprisingly, it was called the strong nuclear force. This force is very strongly attractive and only acts over very short distances. But conveniently, when the nucleons become very close together, it turns into a repulsive force. This stops the nucleons piling into each other until they go out of existence. Since that time, many high-energy colliders have been built to probe into the structure of the atomic nucleus. They have concluded that protons and neutrons are made up of quarks. These are believed to be nearly pointless fundamental particles that have fractional electric charge and cannot be isolated outside of a nucleus. A proton is made from 2 up quarks and a down quark, and a neutron consists of 1 up quark and 2 down quarks. The strong nuclear force binds quarks together inside nuclei. So we now have the basic fundamental particle constituents of normal atomic matter. That is the electron together with up and down quarks that make protons and neutrons. But as you can see, the high-energy collider experiments have shown that there are many other fundamental particles that are unstable, and particles called force carriers such as the photon and the gluon. The photon carries the electric force between electrically charged particles, and the gluon carries the strong nuclear force between nucleons. Unfortunately, we are still not done with the number of fundamental particles and forces required to describe the universe. There is another weak nuclear force that we do not have to go into here, that is required to explain nuclear transformations. And we have one huge outstanding problem: how to explain mass and gravity. Literally billions of dollars have been spent on particle colliders like the Large Hadron Collider to try and come up with an explanation. The idea being pursued is that in the same way that there is an electromagnetic field present throughout the universe, there is also a Higgs field throughout the universe. You can think of the Higgs field as an ocean of water. Some subatomic particles like photons can be thought of as being very streamlined, and move through the Higgs field very quickly at the speed of light. Other matter particles are not streamlined and encounter resistance as they move through the Higgs field. This slows them down, giving them the property of inertia. And that gives them their mass. Once particles have mass, they can be attracted to each other by the gravitational force. So how do you demonstrate that a field actually exists? Well, in the same way that a photon is an excitation, a disturbance, in the electromagnetic field, then it should be possible to create an excitation in the Higgs field. And this is what the excitement was all about in 2012. The Higgs boson with the required properties was discovered in collider experiments at CERN. This arguably completed the standard model of particle physics. However, the current search for the graviton, the particle that carries the gravitational force, is still ongoing. Now we are starting to see how important fields are. Without the Higgs field, particles would have no mass, and the idea of gravity would be meaningless. The universe itself would be unrecognizable, assuming that there were any sentient beings to recognize its existence. And the electromagnetic field. It is over 200 years since Michael Faraday discovered it. And our understanding of this field is responsible for the existence of all the modern power generation and electronic technology that we take for granted today. So although we look at reality in terms of particles, fields are pretty important. Up until now, we have begged the question of where the energy, space and time that allows these particles and fields to exist comes from. We need to look at the Big Bang. Before 13.7 billion years ago, the universe did not exist. Then in some inexplicable way, all the energy to make time and space burst into existence at a single point. This incredibly hot singularity expanded and cooled. The Higgs field switched on and what were massless particles received their mass. Then the universe entered an inflationary period when it expanded faster than the speed of light. At the end of this period, everything had cooled off sufficiently for the constituents of atoms to form. However, the universe entered a dark age, because this ionic soup absorbed all light. Then, about 400 million years ago, the first stars began to shine. Since then, all the galaxies, stars, and planets that we see around us have developed. Today, an unknown source of dark energy is pushing an accelerating expansion of the universe. It is unknown whether this expansion will go on forever, leading to a cold dead universe, or if mysterious dark matter will halt the expansion, and force the universe into contraction. This might lead to a big crunch, at which point everything will just disappear out of existence. Or maybe it will just bounce back. Nobody knows. This story of particles and space is amazingly complex. And there are huge inconsistencies that scientists are aware of. However, these are not generally aired in public. Because there are no satisfactory answers. At least not at the moment. So what are these questions and inconsistencies? Let's start with the very large, and then look at the very small. Recently, observations of the early universe using the James Webb Telescope appear to show galaxies that have not had sufficient time to develop from the commencement of the Big Bang. This has led to speculation that perhaps the Big Bang never happened. Certainly, new improved models of the early growth of the universe need to be constructed. The universe is also currently seen to be expanding ever more quickly. A mysterious dark energy is considered to be responsible for this. But there is no known source of this energy. Amazingly, the amount of this mysterious energy comes to 68% of the total mass energy in the observable universe. And from observation of the motions of galaxies and gravitational lensing, it is believed that mysterious dark matter, a form of matter that does not interact with light, makes up a further 26.8% of the mass energy of the universe. This leaves us with an explanation for just 5% of the universe's mass energy. This is mind-blowing. The standard model of the universe doesn't explain 95% of it. So let's have a look at the very small. The normal matter that we see around us is built essentially of quarks and electrons. Rather disturbingly, quarks cannot be studied outside of protons and neutrons. And they are believed to be point particles. Whatever that means. And free electrons have no measurable dimensions and are usually described by wave functions that define their orbits in atomic structures. So we have a particle theory of reality where particles have all but disappeared. And, in spite of this, we also have a whole zoo of subatomic particles. The fermions are the building blocks of matter. Gauge bosons are force carriers that allow for interactions. Photons carry the electromagnetic force. Gluons carry the strong nuclear force. W and Z bosons carry the weak nuclear force. And in the search for gravity, we need Higgs bosons and gravitons. So our best description of reality requires all these particles. And four forces of nature. Just to describe 5% of the universe. Add to this, that this narrative says nothing about the nature of life and consciousness. And we must admit that we have a pretty poor understanding of the nature of reality and our place in the universe. The question is, can we do any better? Perhaps starting off with fields rather than particles will give us some better answers. So let's have a go. People who aren't physicists may feel that talking about fields is going to be heavy going. But fields are all around us, and we are all familiar with them. It's just that we take them so much for granted. This blue circle represents a blue field. There is nowhere within this circle where there is no blue. We always have to remember that there are no gaps in fields. This particular blue field is very boring. It is what we call a flat field. There is only one value, one intensity of blue. Here we have a much more interesting blue field. It has different values of blue. This contour map, that we are also familiar with, represents a height field. The contours join together areas that have the same height. It allows us to visualize the terrain. We can see low-lying areas that might flood, and when the contours are very close, very steep hills. Again, there are no gaps in this field. There is nowhere on this map, or in the terrain that it represents, that does not have a height. Scientists and engineers use fields to help them explain different phenomena. Hence earlier we mentioned the Higgs field and the electromagnetic field. So how might we build an interesting universal field? Let's start by building a blue universe. We need something to build it from. So we are going to use blue quanta. These are tiny bits of blue that are so small that they barely exist, but happily there are countless numbers of these blue quanta. So as we add more and more together, we build up a nice strong, uniform, flat universe. If we shift some of the quanta around, so that we have high and low values of blue, then we generate an interesting blue universe. We haven't indicated the size of this blue universe. It could be anything we choose. But later we will find that it is useful to think of fields that are infinite in extent. So putting the outward-facing arrows around this blue field indicates that the field is infinitely large. So here we are illustrating an infinitely large blue universe. This is all very fine, but we are pretty certain the universe isn't made out of blue quanta. So what sort of quanta could it be made from? Can we get away from the idea of particles? A good place to start is to look at the ideas of Alfred North Whitehead. He is a famous philosopher. He worked in the early years of the 20th century. His work is highly complex and known to be difficult to understand. But his basic idea is very simple. He suggests that the universe is made from some sort of process. That is some sort of happening. Some sort of action. Now this sounds very unsubstantial, but strangely enough, this is exactly what we want, because we want to get away from the idea of particles and substance. Another reason process might be useful is that we make things with processes. We have process industries, with which we make all manner of goods. We have processes for building cars, ships, planes and computers. And even our food is processed to keep it fresh and eatable. The question is, can we think of a process to build a universe? We want it to be as simple as possible, and it needs to be a quantum process. Here is a representation of an infinitely large quantum process universe. We will represent it in gray. And just as the blue fields we looked at earlier were made from quantum blues, this process field is built up from quantum processes. The problem is to identify a useful dynamic quantum process. And it turns out that a very simple quantum process, consisting of a pair of oscillating quantum electrons, fits the bill. Let's just extract one of these quantum processes from the whole universe. This process is dynamic because the like charges repel each other. So the two quantum charges move apart. Eventually the quantum charges reverse direction as they come under increasing force from quantum electrons in surrounding quantum processes. When the quantum electrons become close together again, their mutual repulsion forces them apart. So the oscillation is self-sustaining. So what sort of universe can we build with this simple process? It doesn't look particularly inspiring, but it has some remarkable properties. To help us see them, we need to appreciate the idea of interfunction. We are familiar with the idea that many things are interconnected. So if you double the speed of a train going from Manchester to London, you will halve the time taken for the journey. We would say that the two are interconnected. However, interfunction is a super-interconnection. It is defined as a relationship whereby the very existence of one thing depends upon the existence of another. So for instance, here we have 2 points representing the positions of the quantum electrons. Now the distance between these two positions is interfunctional with those positions. If either position did not exist, then the distance between them would cease to exist. And importantly, if the distance between them did not exist, then the positions themselves would become meaningless. Let's see how this idea of interfunction gives this oscillating quantum process tremendous power. We need to look at its properties and interfunctions. So, because electrons have mass, our quantum process has quantum mass. Electrons have electric charge, so our quantum process has quantum charge. Our quantum electrons are moving, so the quantum process has quantum electrical energy. Our quantum electrons force themselves apart, so our quantum process has quantum force. When the quantum electrons are moving, they have quantum kinetic energy, so the quantum process has quantum kinetic energy. When the quantum electrons are fleetingly stationary, they have quantum potential energy. And because our quantum electrons are separated, the quantum process has quantum distance. The oscillation takes place in time, so the quantum process has quantum time. Because the quantum electrons reflect at boundaries, the quantum process has quantum boundaries. When the quantum electrons reach their boundaries, they have to be aware of the existence of those boundaries in order to reflect at those points. So the quantum process has quantum awareness. And because the quantum process is aware of the distance between its boundaries, it has quantum self-awareness. If we define sentience as something having the property of awareness of other as well as self-awareness, then our quantum process has quantum sentience. This is an impressive list of properties for one incredibly small and simple process. But we have not quite finished. When electric charges move, they generate magnetic fields. So when our quantum charges move, they generate a quantum magnetic field. So our quantum process generates quantum magnetism. This magnetic field is generated in a two-dimensional plane at right angles to the oscillation. So our quantum process generates a total of 3 dimensions of space. We need to appreciate that these properties are also interfunctions of the process. This picture illustrates just some of the interfunctions that we have just talked about. In the center is the quantum process, and around it are some of the process's interfunctions. The lines connecting them all together remind us that they are indeed interfunctions. And if any one of these properties did not exist, then none of them could exist, including the master quantum process that encapsulates them all. So let's put our quantum process back into our universal quantum process field, and see where the interfunctional properties of all the quantum processes take us at the universal field level. We still have the universal quantum process field that we looked at before. But now we are aware that this field is a master field, and it has a whole host of other interfunctional fields associated with it. There are many important observations that can be taken away from this diagram. On the right-hand side we see that a three-dimensional space field is an interfunction of the process field. This is incredibly important. We have an ongoing process that generates three-dimensional space. This is the crucial difference between a particle and space view of reality, and a quantum process field view of reality. In the particle and space view, space and time have to miraculously come into existence in a Big Bang from nowhere. And in doing so all the rules of conservation of energy are broken. In the quantum process field view of reality, three-dimensional space and time are continuously supported by countless numbers of ongoing quantum process oscillations. Another amazing consequence that we can take away from this diagram is that in the same way that universal space is generated by the universal quantum process field, universal sentience is also generated by the same process. The implications of universal sentience are incredibly far-reaching, but we do not have the space and time to follow that particular thread here. The numbered videos in the playlist Reality and Consciousness from Quantum Processes and Holons investigates some of the possible implications. It is worth noting, however, that the particle and space view of reality says nothing about consciousness and sentience, whereas sentience and consciousness are an integral part of the quantum process paradigm. But we need to get back to the physical universe. When we look at the quantum process fields, they are okay as far as they go, but they are uninteresting, flat fields. So how does our amazingly complex universe with all its incredible detail develop out of this flat universe? We are used to the idea that we are surrounded by objects, solid things made of particles. And even though we saw earlier that these particles have a most tenuous existence, we pretty much cling to the idea that we, and all the things that we see around us, are made from solid objects. It is so natural that we never think to question it. But there is another, better way, of looking at reality. And it rests upon coming to an appreciation of boundaries. When we sit down and look around, we see and feel boundaries. In this picture there are numerous boundaries that define all sorts of objects. The bed has a boundary and it consists of other objects that have boundaries. The bedhead, the pillows, the mattress. The hat has its boundaries, and also the television. And that consists of many complex components that have their boundaries. These pebbles have very fixed, distinct boundaries. But the beach has variable boundaries as the tide comes in and out. It consists mainly of sand grains, and these too have their boundaries. So why this obsession with boundaries? Well, one of the interfunctional quantum process fields is the quantum boundary field. So is it possible that all these boundaries that we see around us are built up from quantum boundaries? We know that all objects are made from atoms. So if we can build an atom from quantum boundaries, then we can build everything else from quantum boundaries. Here on the right is a representation of a single quantum process. On the left are some of these quantum processes aligned to form a circle. Align these quantum processes in 3 dimensions, and you form a spherical shell, an enclosure with an inside and an outside. If we add even more quantum processes to form inner boundary shells, a cross-section through the shells looks something like this. So why would quantum processes in a completely random field of quantum processes align themselves in this way? Well, this radial alignment allows the outer quantum shell to expand away from its center, because the aligned forces from the inner quantum charges push against the randomly orientated outer quantum charges. At some point equilibrium is restored, but all the inner quantum processes have more space for themselves. In terms of quantum awareness, you could say that quantum processes have an innate driving force to grow, rather than be squeezed out of existence. But the story of the emergence of life and consciousness from these quantum beginnings is set out in other videos on this channel. So going back to the atom building process. Here is the magnetic circulation around one of the quantum processes that form the outer shell. It shows magnetic circulation going into the screen as red and out of the screen as green. And, when these clockwise and anti-clockwise rotations are delocalized and added together, they form 2 counter-current magnetic circulations around the atom. There are of course countless numbers of these circulating magnetic rotations. and their interactions are very complex. But we end up with an atom looking a bit like this. We have quantum magnetism circulating in two directions and quantum charge oscillating radially. If we illustrate the charges in an arbitrary blue color, and add them to the magnetic circulations, red and green, we have an illustration of how atoms are made from trapped light, strictly of course trapped electromagnetic radiation. So, here we have described the creation of a hydrogen atom's s1 ground state orbital from a random quantum field. You may have expected that the fourth disk would be colored white to illustrate the wide range of the electromagnetic spectrum. However, it is colored black because the electromagnetic radiation that makes the atom is trapped and cannot escape. So to an outside observer, an unilluminated atom is black. Of course, all matter is black. Matter can only be seen if it is illuminated from an outside source or is stimulated to emit light. We merely have to switch off the light sources in a room to prove the point. Real atoms, of course, are far more complex. But here we are just describing a basic theoretical idea of atoms that can be developed to explain the structures of other atoms and molecules using quantum mechanics. So what happens if we have a look at objects that are very large and very small compared to an atom? The Sun is a pretty big object. On the left-hand side, we are looking at a photograph of a sunspot. You would imagine that the Sun and the nature of sunspots would be pretty well described by conventional science. But there are many unexplained problems. The most glaring one, or should it be an unglaring one, is that sunspots are black. How come the inside of the Sun, which should be even hotter and more brightly glowing than the outside, is black? This obvious discrepancy is glossed over, and flies in the face of the standard model of how the Sun is meant to work. However, if we apply the quantum process field view of reality, we would expect the inside of the Sun to be black. Because the Sun, like everything else with a boundary, is made from trapped electromagnetic radiation. Trapped light. The Sun also has a highly complex and time-dependent magnetic field, the origins of which are currently poorly understood. But in the quantum process field view of reality, it is not surprising that the Sun has a powerful and complex magnetic field. Its very structure is electromagnetic in nature. In the future, solar cycles, flares, and coronal mass ejections may be better understood using a quantum process field view of the Sun's structure. So now let's have a look at things that are very small compared to an atom. We are going to use the concept of holons. They have a big part to play in quantum process field theory, not least that they provide a route for explaining life and consciousness. But here we haven't the time to do holons justice. We are merely going to use the term holon to describe objects made from multi-layered boundaries. A bit like how an onion is put together. So here is our atom again, but this time we will call it an atom holon. It is possible to calculate the quantum electron speeds of the quantum processes that make up the shells of this atom holon. It is also possible to calculate quantum electron speeds inside smaller holon spheres that represent subatomic particles. And if you do this, you can generate this diagram. The vertical axis is shown as a log scale to fit in the enormous range of quantum holon sphere diameters. And the horizontal axis is the fraction of all the quantum charges that have speeds greater than the speed of light. So the diagram shows sphere diameters that have virtually no quantum electrons exceeding the speed of light, up to sphere diameters having all quantum electrons exceeding the speed of light. Now, as far as we know, no objects in the universe can exceed the speed of light. So we will test out an idea on this diagram. We will take it that if the speed of quantum electrons in a process oscillation exceed the speed of light, then that quantum process cannot be held inside that quantum sphere's boundary. In effect, the quantum process escapes the holon sphere, taking its quantum space with it. This proposal enables us to make some predictions. The green line represents sphere diameters above which virtually no quantum charges exceed the speed of light. And the red line on the diagram indicates sphere diameters where all the quantum charges exceed the speed of light. So we can predict that sphere holons with diameters greater than 1.63 times 10 to the minus 14 meters are stable within normal time frames. And that sphere holons less than 1.39 times 10 to the minus 17 meters do not exist. Spherical holons between these two limits will be unstable. We need to put the diameters of some real spheres onto the diagram to test the idea. Here are two sphere diameters corresponding to the diameters of a helium and a cesium atom. Both of these fall well within the stable range in our diagram. So what about holons the size of atomic nuclei? The uranium-238 nucleus holon falls in the unstable region, but has a long half-life of 4.5 billion years. In contrast, the much smaller neutron has a half-life of just 15 minutes. So what about even smaller spheres? This diagram shows a proposed schematic for a beta decay, where a neutron decays into a proton, an electron, and an antineutrino. But all we want to illustrate here is that the extremely small antineutrino particle corresponds to an extremely small, super-unstable Holon sphere. This quickly loses all its quantum electrons and quantum processes of which it is composed, and decays out of existence. This accounts for why detecting these particles is so difficult. Very importantly, this quantum process field view of reality is able to predict the stability of matter and the nature of radioactive decay. This is something that the particle and space view of reality is completely incapable of doing. We can also ask, what happens to the quantum space carried off by escaping quantum processes? Preliminary work shows that the positions of quantum electrons escaping from holons follow the mathematics of chaos. Quantum charges in very small, neutrino-sized holons move away from each other to positions vastly far away from each other and their originating holon. This leads to an intriguing possibility. Does the quantum space of escaping quantum processes add quantum space to surrounding universal space? If so, this would increase the distance between objects, such as galaxies, forcing them further apart. Could this be the source of dark energy? A mechanism to account for the observed expansion of the universe. And another useful fact emerging from this quantum process field model of reality is that knowing the proportion of quantum electrons escaping from hydrogen atom holons, it is possible to calculate the gravitational force of attraction between two hydrogen atoms using only the electric force. The details are set out in Reality and Consciousness, Uniting the Forces of Nature, on this channel. So the quantum process field view of reality has some rather amazing properties. Not least that it can explain the reality that we see around us very simply, using very few initial assumptions. On the left is a summary of the particle and space view of reality. Scientists are left struggling with four forces of nature: the electromagnetic force, the strong nuclear force, the weak nuclear force, and the force of gravity. There is no explanation for the wide variations in the properties and strengths of these forces. We also have to accept that the universe and time started out with an unexplained Big Bang, which completely breaks all the rules of the conservation of energy. And we have to contend with an ever-growing zoo of subatomic particles. And all this to explain just 5% of the universe. On the right is the quantum process field view of reality. It too explains reality, but it does it in a much more concise way. It uses just one force of nature, the electromagnetic force, and one master process field made from simple oscillating interfunctional quantum processes. If simplicity of explanation is a measure of how to choose the best of competing theories, it is easy to see which one to choose. Of course, the interfunctional quantum process field theory is very new and conceptual. But in the quest for understanding reality, there are many reasons for pursuing the idea. We have only been looking at how reality can be explained with quantum processes. We have not really touched on the amazing ability of this quantum process paradigm to explain awareness, life, consciousness, and the human condition. If you want to find out more, these topics are covered in the numbered videos in the playlist Reality and Consciousness. I hope you have enjoyed this video. Please like and subscribe, and please tell your friends about it. Thank you for watching.